All right, at the end of last week, we were talking about light as a wave, and we saw wavelength and frequency and how it related to the type of light and the color of light. So again, notice long wavelength light is radio waves, and that long wavelength has a very, very low frequency. Very short wavelength light is over here in gamma rays, which means it has high frequency. And so you go through the whole spectrum: radio, microwaves, infrared, visible light, Roy G. Biv, then ultraviolet, X-ray, and gamma ray. Notice a visible light, the longest wavelength, lowest energy is red. Now, they talk about energy here, and when we were talking frequency, that's an issue because wave theory doesn't predict that. Wave theory says that energy should relate to amplitude, the brightness of the light source. But here they're showing it as energy correlating along with frequency. Low frequency means low energy. And that's a problem. Now, the evidence we have for that is something that the book doesn't mention, called black body radiation. If you take an object, say a black iron cannonball, and warm it up, it will maybe be infrared hot. It'll glow infrared bright. Your body glows infrared bright. Some of you might be really cold, I don't know, but most of you are infrared emitting, which is why police use those infrared cameras to find people at night. If you continue to heat up that iron bowling ball, it will eventually start emitting red light. It'll glow red hot, and then orange, and then yellow, like our sun, for example. And so on. Eventually it gets to blue hot even, and further. So as you add heat energy is the key word there, the object emits light at a higher and higher frequency. So notice that energy correlates with frequency, and that's not something that wave theory of light predicts. So there's something wrong with wave theory there, and we're going to have to deal with that eventually. But let's continue on for the moment. The book now looks at something else that was occurring with the spectra of glowing objects, or absorbing objects, called spectroscopy. This is again something that wave theory of light and the standard atomic model of the time, Rutherford's model, didn't predict properly. If you take normal white light from a light bulb like they show here, or from the sun, and pass it through a prism, you'll get Roy G. Biv, the whole spectrum. But if I take a gaseous sample of substance, in the example here they're using helium, and you let it glow, maybe you heat it up, maybe you just pass electricity through it like they do here in a gas discharge tube. Neon light tubes do this. Fluorescent light tubes do this. So you pass electricity through the gas, you give it energy, and it glows. But different gases glow different colors. Helium glows this like yellowish color. Neon glows the characteristic reddish-orange color. Copper glows green. So every element has its own color that it glows. If you pass its light through a prism, you'll find that it doesn't emit all of Roy G. Biv. It emits certain specific colors. And here they show the specific colors that helium emits. It has a nice red line, kind of an orangish line, a yellow line, and so on. But it doesn't emit colors in between here. So yes, it has a green line, but other shades of green it's not emitting at all. And no one knows why that, or at the time, no one knew why that was the case, because theoretically it should emit all colors of light, not just certain selective colors. Even more interestingly, all helium does this exact same pattern. If I go to a different element, like hydrogen, it's a totally different pattern. There's a red line, and like an aqua line, and two violet lines. So they discovered in the 1800s that this actually acts as a fingerprint for the elements. Anytime I see this pattern of lines in a light spectrum, I know there's helium there. So they use that, like in astronomy, they can pass the sun's light through a spectroscope and see these lines in the spectrum, and that's how they know the sun is made of hydrogen and some helium. No one's ever landed there, not even at night when it's cooler, right? They do it by looking at the lines in the spectrum and identifying the fingerprints of the elements. But again, at the time, they had no clue why it was doing this. And this is, again, the information that led Bohr to propose his theory with the quantum jumping of the electrons that they introduced you in the beginning of the chapter. Again, if I was doing this in class, I would have rearranged this and covered this first, because I think it makes more sense that way. This slide, they're just explaining what I just talked about. An atomic emission spectrum is exactly what we were looking at, those lines in the spectrum. When you feed energy into a gaseous element, it will emit certain lines of bright lines of color, and that's an atomic emission spectrum. And again, I said it acts as a fingerprint. They word it as no two elements have the same spectrum. Okay, so now, for no apparent reason, they give you two examples of that speed of light equals wavelength times frequency that we did yesterday, or well, Thursday, I guess it was. So real quickly, we'll go back and look at this because I'm going to include some more of this on your homework for today. They give you a frequency of light, and you need to find the wavelength. So speed, well, you know the speed of light, you know the frequency, you're looking for the wavelength. Speed of light equals wavelength times frequency. Plug all the numbers in, they rearrange first, and you get 5.89 times 10 to the minus 7th meters, which we could translate into nanometers if you want. Doing it the other way, they give you nanometers wavelength, ask you to find the frequency. Again, plug in, rearrange, and you don't forget you have to convert it to meters from nanometers, and you get the frequency. We did this on Thursday, so I'm not going to waste your time going with a lot of detail on it again. But it's a quick reminder of those math problems we did, and we'll continue to do. So, these lines in the spectrum have certain specific frequencies and wavelengths. In fact, on the previous example, this particular line that they used ends up being at 589 nanometers. Where's the answer they gave us? There it is. 589 nanometers. That exactly is the bright yellow line in the sodium spectrum. So again, you can take that reddish line that was in the helium spectrum, and you can measure its wavelength and calculate its frequency and all the other fun stuff. So that's that. Now, another interesting thing that was a problem at the time was the photoelectric effect, which I don't want to get into too much depth with here because we're running low on time for the year. But the basic idea is if you take a piece of metal and you shine light on it, electrons get ejected off the surface of the metal. And the way it was working didn't agree with the predictions of wave theory. So, a guy named Max Planck comes along and proposes new mathematical formulas that he calls quantum theory. And what he found, among many other things, was that the energy of light equals some constant that he called h times frequency, nu. So E equals h nu. And this is Planck's equation. That constant h is called Planck's constant. Now, it doesn't seem like a big deal. It's just the energy of light relating to its frequency. But notice that exactly agrees with what we saw back on the spectrum slide, where low energy red light was low frequency red light. And with the photoelectric effect, or I'm sorry, the black body radiation in general, where cold or low energy objects emitted low frequency infrared light, whereas hotter objects started emitting higher frequency red, orange, yellow light. So the energy relates to the frequency. Now, the big deal here, though, is the energy of what? Just light vaguely? Well, no, specifically the energy of a piece of light. Now, that doesn't sound very scientific, so he called it a quantum of light, which we nowadays call a photon. Quantum is a Latin word meaning amount or how much. So, bottom line is, Planck is saying that light is no longer made of waves. Light is made of little tiny, really, particles. He didn't want to use that word because that was kind of a bad thing back in those days. Light was not a particle, they thought. But clearly he's saying light's not a wave. It acts as little tiny particles that he called quanta, because he didn't want to use the word particle again. Later, Einstein came along and said, let's call them photons, and so now we do. Because why would you go against Einstein, right? So the energy of a photon of light is equal to Planck's constant times the frequency of the light. So if you know the frequency, you can plug in, find the energy of that photon. It's going to be a really tiny energy, like 10 to the minus 19th or so joules. But that makes sense. Electrons, protons, and neutrons have a small amount of mass. So photons, particles of light energy, are going to equivalently have a very small amount of energy. So Planck's constant is this number right here. I don't know why they carried it over. It's not really a good idea to do that. 6.626 times 10 to the minus 34th joule seconds. Okay, so notice Planck's constant is an extremely small number, 10 to the minus 34th. This is another one of those constants where I'd ask you to memorize this if we were sitting in class taking quizzes all together, but you're at home on your own. If you write it down beforehand, I'm not going to know. Okay, so but you'll want to, in the long run, know the value of Planck's constant. It's an extremely important physical constant in our universe. Now, I talked briefly about the photoelectric effect, ejecting electrons from the surface of metal when light hits it. It turns out Einstein proved mathematically that the way the photoelectric effect works agrees exactly with Planck's quantum theory. So Einstein basically showed that Planck was right by using this photoelectric effect, which again I'm not going to get into detail in because we just don't have the time for it. So let's go on and do actual calculations. Again, notice photons are the term we now use for these quanta of light. Okay, again, I don't want to get into the detail of that, but let's look at the math a little bit. Here they give us a light wave with a frequency of this. It's microwave, so it's very low frequency, and that means low energy. Okay, so what's the energy of the photon? Well, let's plug into the equation. E equals h nu. We know the frequency because they just gave it to us. We know Planck's constant because we've memorized it. And so we want to find the energy. So E equals h nu. We plug in the Planck's constant that we know. We plug in the frequency they gave us. There they do it. Multiply them, and we get an energy of that. 2.12 times 10 to the minus 22nd joules. It's an extremely small amount of energy because it's a microwave photon, and those are low energy photons. If this had been visible light, the answer we would have gotten would have been like 10 to the minus 19th. Maybe if it was like ultraviolet, 10 to the minus 18th. The exponent gets bigger, closer to 0 because it's a negative number. Okay, so that's really that. Now, does the result make sense? Yeah, it's a photon. It's an individual particle, so you're going to expect a very small answer. Just like if I ask you about the mass of an electron, you would expect a very, very small amount of kilograms because it's a tiny particle. Okay, let's do one the opposite way. They give us the energy of a photon. They want you to find the frequency. Well, again, E equals h nu. Plug in, again, they rearrange the equation first, but you can easily plug the numbers in first and solve. And you find the frequency equals the energy over h. So plug in the energy, plug in Planck's constant, divide them, and you get this very, very high frequency. You'll recall last time we saw visible light ended up with frequencies of like 10 to the 14th-ish hertz. So this is a very, very high frequency light. That makes sense. It's much, much higher energy than visible light also. So that is the new equation for today, and we'll come back to that atomic spectra stuff tomorrow. So what I'm going to have you do for the rest of today is I'm going to give you a few problems where you have to use Planck's equation. I'm going to throw some in there where you also have to use the previous equation, C equals lambda nu. For example, if I give you the frequency, ask you to find energy, you just plug it in, life is good. But what if I give you the wavelength and ask you to find the energy? Well, wavelength doesn't fit in here. But we have that old equation, C equals lambda nu. We can plug into that, use the wavelength, find the frequency, and now we have the frequency, we can get the energy. Okay, so I want you to try that tonight, and then we'll continue on tomorrow. And that's it for today.